Hello, my name is Daniel Weldemariam, and in this presentation, I'm going to discuss about the fabrication and applications of carbon nanotubes. All right, I will start by briefly introducing nanotechnology and carbon nanotubes. Next, I'll cover the characteristics of carbon nanotubes, which will provide, I believe, theoretical background needed to understand these materials. Then I will discuss the main fabrication methods for synthesizing carbon nanotubes, focusing on the three most important techniques. After that, I will touch on the various application areas where carbon nanotubes are used. Finally, I will conclude by highlighting the opportunities and challenges facing carbon nanotubes and summarize the key points of my presentation. I hope you're going to like it, so stay with me. Nanotechnology, which is the science of working with tiny particles, has seen huge growth in the 21st century. So scientists are now able to manipulate matter at an incredibly small level, like atomic and molecular level. Among the most promising materials, carbon nanotubes have emerged as a groundbreaking materials for both fundamental research and technological innovation. They were first discovered by Japanese scientists named Sumito Iijima in 1991 at the NEC laboratories in Japan. These carbon nanotubes are cylindrical structures made of carbon atoms arranged in a hexagonal lattice, similar to a single layer of graphene. What makes them different is they're like rolled up sheets of graphene that has diameter in the nanometer scale. Carbon nanotubes has got remarkable electrical, mechanical, thermal, as well as chemical properties, which makes them ideal for a variety of applications in a range of industries. Now, let us see the characteristics of this amazing materials called carbon nanotubes briefly before moving into the fabrication part. As I said earlier, the rolling of graphene creates carbon nanotubes. So this rolling is called chirality, and it introduces a curvature to the structure. And the way the graphene is rolled leads to a unique electrical, mechanical, and thermal properties. So, based on chirality, the resulting carbon nanotubes with distinctive electrical properties can be classified as zigzag, armchair, and chiral, as you can see here on the diagram. When N and M are just vectors on the X and Y direction. So we can represent how the graphene is rolled based on these vectors. So if N and M are equal, like this one, the resulting carbon nanotube is called armchair. If either of N or M, like in this case N is 0, it is called zigzag. Otherwise, the resulting carbon nanotube is called chiral. But we should only note that not only their name, but their properties are also affected by this chirality. For example, if N is equal to M, the nanotube is metallic, and if N minus M is a multiple of 3, then the resulting nanotube is semiconducting. So the same material, but based on how the graphene is rolled, which otherwise means chirality, we can get different characteristics of the same material. So it's one of the most important characteristics of carbon nanotubes, as we will see on the application part later in this presentation. The other magnificent characteristics of these tiny materials is they are 50 times stronger than steel, and yet they are only a quarter dense as steel. So it's really incredible, and it has got a lot of applications with this behavior as well. The major and most important classification of carbon nanotubes is based on the number of layers. Based on this number of layers, they are classified as single-walled carbon nanotubes and multi-walled carbon nanotubes, as you can see here on the picture. So let's see in detail. Single-walled carbon nanotubes, they are made of a single layer of graphene rolled into a cylinder, whereas multi-walled carbon nanotubes, as you see, There are multiple layers of graphene arranged concentrically. In terms of diameter, the singles are typically between 0.4 to 2 nanometer, which is quite small, whereas the multi-hole carbon nanotubes, their diameter range between 2 and 100 nanometer, which is a little bit higher than the single-hole carbon nanotubes, but still at very low diameter in the nanometer scale. Electrically, single-hole carbon nanotubes can be either metallic or semiconducting, depending on the chirality. As we have discussed on the previous slide, the chirality of the carbon nanotube decides the behavior of the resulting material. So multi-hole carbon nanotubes, on the other hand, they are primarily metallic. Mechanically, single-hole carbon nanotubes has got high strength and stiffness, whereas their counterpart multi-hole carbon nanotubes has high strength and stiffness, but generally lower than the single-hole carbon nanotubes. Chemical reactivity, as you know, it is based on the surface area of any material. So single-hole carbon nanotubes has got higher reactivity due to the fact that they have larger surface area, whereas multi-hole carbon nanotubes has got lower reactivity compared to single-hole carbon nanotubes, but still they are very reactive, just to compare the two. Production challenges, in order to produce both any kind of carbon nanotubes, it's really a complex process. But comparing these two, producing single-hole carbon nanotubes is more complex to produce in a pure form, and multi-hole carbon nanotubes are relatively easier to produce. Applications, the single-hole carbon nanotubes can be used in electronics, sensors, composites, energy storage, like we have seen electronics and sensors, because they can be semiconducting as well. And multi-hole carbon nanotubes can be used in composites, filtration, and environmental applications. Now let's see the fabrication of carbon nanotubes, which is the most important part in this presentation. Generally, there are only few techniques employed to produce carbon nanotubes. So in this presentation, I will cover the three most important and well-known methods of synthesis of carbon nanotubes. These three methods are arc discharge, laser ablation, and chemical arc deposition. Now, let me start with the electric arc discharge method. Electric arc discharge method is the oldest and most common method of fabricating carbon nanotubes. In fact, Ijima, who discovered carbon nanotubes, introduced this method. He used this method in order to produce the first carbon nanotube. This method involves creating an electric arc between two carbon electrodes in an inert gas atmosphere, such as helium or argon, as you can see on the picture. We have two carbon electrodes as anode and cathode, and in this vacuum chamber, we've got helium or argon, which is an inert gas. The high temperature generated by the arc causes the carbon to vaporize, and then as the carbon cools, it condenses into the carbon nanotubes on the electrode surface and surrounding walls. As you can see here, we have electric voltage here. It helps us to heat this anode and cathodes. So it vaporizes the carbon and produces carbon nanotubes on the surrounding wall, as can be seen here clearly. So the high temperature generated by the arc causes the carbon to vaporize, and then as the carbon cools, it condenses into scientists on the electrode surface of the surrounding wall. During this process, a constant current is maintained to produce high quality of carbon nanotubes at high temperature of approximately 4,000 to 6,000 Kelvin. So this method offers advantages such as yield, relatively simple, and the ability to produce both single-hole and multi-hole carbon nanotubes. However, it also comes with challenges, including safety concerns due to high temperature and electric arcs, obviously. Difficulty in controlling the growth process and energy consumption, because we use high temperature and electric arcs, we definitely need more energy. Additionally, this method often produces impurities that require further purification steps, as it is the first method deployed in producing carbon nanotubes. It's expected that we may not have a pure carbon nanotubes, as we will see in the other fabrication methods. Despite these limitations, the electric arc discharge method remains a valuable tool for carbon nanotube research and development. The second fabrication method I like to cover is laser ablation. Laser ablation is a newer method and produces a high quality carbon nanotube with well-defined structure. Similar to the arc discharge, this method vaporizes the carbon and later deposits it onto a substrate. However, laser ablation uses high-power laser, as the name implies, to vaporize a graphite target, which often is a small amount of metal catalyst, such as nickel or cobalt, in an inert gas atmosphere, like helium or argon. In most cases, inside a vacuum chamber, as you can see here. We have a vacuum chamber, we have a laser source and lens, which help us to direct the laser to this graphite. And as the plasma cools, the carbon atoms recombine to form carbon nanotube. We have a water here, which helps as a coolant. So the inert gas helps to carry the carbon vapor and cool the system. The laser-induced plasma generates carbon vapor, which condenses into carbon nanotubes on a cooled substrate. This is the resulting carbon nanotubes. The quality and yield of the produced carbon nanotubes depends on various parameters like laser power, pulse duration, gas pressure, and target composition. Some of the advantages of laser ablation technique are it offers or produces high-quality carbon nanotubes with minimal impurities. It allows for better control over diameter of the product. The process is relatively fast compared to other methods. It is pretty much versatile because it can be used to produce both single-old carbon nanotubes and multi-old carbon nanotubes. However, it also presents a few challenges, including low yield, high production cost, and safety concerns. That's because it uses high-power lasers. Despite these limitations, however, laser ablation remains a valuable tool for research and some specific applications where high purity of carbon nanotubes are required. The third and most important fabrication technique I like to cover is chemical vapor deposition. Chemical vapor deposition is the most widely adopted technique in the production of carbon nanotubes so far. In CVD, to initiate the process, gases such as nitrogen and another carbon-containing gas such as methane, ethylene, or acetylene are introduced into a reactor containing a catalyst, commonly iron, nickel, or cobalt, on top of substrate like silicon, at high temperature, around between 600 and 1000 degrees centigrade. So the gas decomposes and carbon atoms deposit onto a substrate, forming carbon nanotubes, as you see here on the picture. We have the carbon nanotubes inside a reactor on top of a substrate, and we have catalysts like nickel or cobalt here. So the CVD pretty much may be defined as the deposition of a solid on a heated surface from chemical reaction in the vapor phase. We can say it is a class of vapor transfer process. We should note that the various parameters such as catalyst type, gas flow rate, temperature, and pressure can significantly influence the growth process and properties of the resulting carbon nanotubes. Chemical vapor deposition has got a lot of advantage, like it is relatively uncomplicated and flexible technology, which can accommodate many variations. It uses easily available raw materials, abundant in the form of gases, like you see we use nitrogen here. So with CVD, it is possible to coat almost any shape of almost any size, which is an awesome feature, to be honest, which can be applicable in many situations. You can create any kind of shape using this method. So, and of course, the CVD is economically competitive, which makes it really attractive among all methods we have seen so far. However, there are also a few challenges, like achieving uniform nanotube growth across large areas. That's one of the hurdles facing this technique. Energy consumption is relatively high due to the elevated temperature requirement. Like we said, we need a temperature between 600 to 1000 degrees centigrade. So obviously, it requires a lot of energy. Additionally, controlling the alignment of carbon nanotubes within the growth process presents another challenge. However, despite these applications, CVD remains a cornerstone, I can say, a cornerstone method for carbon nanotube production due to its overall effectiveness and compatibility with various applications. So now we have covered three fabrication methods for carbon nanotubes. So now let's compare and contrast these three methods just in briefly, as you can see on this table. So first, let's see based on the condition, like the type of gas and pressure and temperature they require. CVD uses low pressure intergas like argon, whereas arc discharge, it uses argon or nitrogen gas at 500 torr, which is a measure of pressure. In laser ablation, it requires temperature between 500 and 1000 degrees centigrade, and it uses, as we have discussed, a laser beam, high energy laser beam. Yield represents the amount of output we get compared to the input given. It's like efficiency. So chemical vapor deposition, it has high efficiency between 60 to 90%, and arc discharge, it is quite variable. Sometimes it gives us as low as 20%, and at other times, if we are very lucky, it can give us 100% efficiency, but this one is rare. Most of the time it's below 50%. Laser ablation, it's we can say moderate. We can get up to 70% yield. In terms of purity, how pure the carbon nanotubes we get from the three methods. CVD, we get medium to high purity, whereas arc discharge, it's low to medium, and laser ablation, as we have discussed, always yields us the best quality carbon nanotube, so it has high purity. The temperature requirement, this temperature requirement determines the amount of energy consumption, the cost, so it's really important parameter. So when you compare these three in terms of the temperature requirement, laser ablation requires between 1200 to 1500 degrees centigrade, which is medium. Arc discharge, it is, as you can see here, is about 4000 degrees centigrade, which is really high. And CVD, we use relatively lower, between 500 and 1200 degrees centigrade. In terms of the product, CVD gives us both single-walled carbon nanotubes and multi-walled carbon nanotubes, whereas arc discharge, it usually predominantly used for multi-walled carbon nanotubes, and in small amounts it also gives us single-walled carbon nanotubes. Laser ablation is mostly used for single-walled carbon nanotubes because they have strict quality requirement, and we don't use it for multi-walled carbon nanotubes usually. Now let's see the application of these carbon nanotubes. As we have discussed in the previous slides, carbon nanotubes are remarkable materials that have gained significant attention in nanotechnology due to their extraordinary properties. They possess high electrical conductivity, mechanical strength, thermal conductivity, and chemical stability, which makes them suitable for a wide range of applications across various fields, as we have witnessed in our previous slides. So in electronics and semiconductors, carbon nanotubes are poised to become key components due to their ability to create high-performance transistors that surpass traditional silicon-based devices in terms of speed and energy efficiency. There is also a huge potential in this area, considering the miniaturization capability of carbon nanotube-based transistors, which could enable them the development of smaller and more powerful electronic devices. Energy storage, when it comes to energy storage and conversion, it is another significant area where carbon nanotubes have shown great promise. In lithium-ion batteries, carbon nanotubes enhance performance by increasing charge capacity and extending cycle life. They also have a lot of applications in supercapacitors and catalysts for fuel cells. Moving forward to another excellent property of carbon nanotubes is that they have a strong strength to weight ratio, as we have seen by comparing them with iron in previous slides. So this mechanical property of carbon nanotubes makes them ideal for composite materials, which are used in industries such as aerospace, automotive, and construction. In the field of sensors, carbon nanotubes excel due to their large surface area and chemical reactivity, which enables them to detect gases, vapors, biomolecules with very high sensitivity. And they can be used in areas like identification of hazardous substances and environmental pollutants. So in this arena, they've got pretty much application areas. Carbon nanotubes are also making huge step forward in the biomedical applications, like drug delivery systems inside our body, carrying some kind of drugs or medicines into specific cells or tissues, which has got an amazing potential in the medical field. Environmental applications. Environmental applications like improving water and air quality by removing contaminants is also another application area for these tiny materials. In the textile industry, carbon nanotubes are used to create smart fabrics which integrate electronic functionalities into textiles. These conductive fabrics are employed in wearable electronics. So, what we can say in conclusion is that carbon nanotubes represent a versatile and transformative materials with applications spanning in numerous industries, as we have tried to see here briefly. Carbon nanotubes, as we have discussed, have immense potential since their discovery, and they are promising to revolutionize various industries. Among the opportunities they are expected to bring up in a few years to come are advanced materials, which they can be integrated into composites, coatings, and other materials to enhance their mechanical, electrical, and thermal properties. They're also electronics and semiconducting industry because of their unique electrical properties. They are promising candidates for next generation transistors and electronic devices. Energy storage. Carbon nanotubes can improve the performance of batteries, supercapacitors, and fuel cells by enhancing the energy density and charging rates. Sensors and actuators are also due to the high sensitivity of carbon nanotubes to various stimuli. They enable the development of advanced sensors for a variety of applications. However, despite significant advancements, there are several challenges in realizing the full potential of carbon nanotubes. To mention few, like mass production, achieving consistent and large-scale production of high-quality carbon nanotubes, it remains a significant hurdle. The current methods we have seen so far often result in variations in diameter, length, and structural defects, which affects the overall performance of carbon nanotubes. The other challenge is dispersion and processing. Effectively dispersing carbon nanotubes in a polymer matrix or other materials without compromising their properties really challenging. Cost, obviously. Cost effectiveness, the production of cost of high quality carbon nanotubes is still relatively high, limiting their widespread commercialization. Toxicity and environmental impact. Also, studies suggest low toxicity. The potential of long-term health and environmental effect of carbon nanotubes require thorough investigation and mitigation strategies. In summary, as these hurdles are overcome, carbon nanotubes are expected to play a crucial role in the next generation of technology. So continued research and development are necessary to address these issues and pave the way for a widespread commercialization of these magnificent materials. Well, that's all for today. Thanks for staying with me.